Hi guys, we're going to finish up our chapter 13 with chapter 12 and 13 with phase changes and phase diagramming. These notes, the slideshow, is part of your liquids and solids PowerPoint that I posted earlier. So you'll find that, I think it's slides like 16 through 30. So we're going to go through those now, okay? In terms of an objective, I think that maybe in all of the classes we started to talk just a little bit about phase changes. I want us to be able to explain how the addition or the removal of energy could cause a phase change. So if we add energy or we could remove energy from a system, and that is why phase changes will occur. I also want us to be able to interpret phase diagrams, which is something that will be new. And then just as a review, phase change, we've heard of that before, and that's just when we have a change from one state of matter to another. So like moving from a solid to a liquid, or from a liquid to a gas, or from a gas to a solid. So we've heard those before, but now we're going to really talk about the process of each one. So first one is melting. We're going to focus on melting first. And melting occurs when heat flows into a solid object. So when an ice cube is placed in water, the water is at a higher temperature than the ice cube is. So heat is going to start to flow from the liquid water into the ice cube, because the liquid water would be warmer since it's a liquid, and then that ice cube would be cooler. So heat will always transfer from from an object at a higher temperature to an object at a lower temperature. So melting occurs because heat, which we know is just energy, is being moved or being transferred from something that's at a higher temperature to something that's at a lower temperature. So if I have ice cubes in water, my water is going to transfer heat into an ice cube. And that's what's going to cause this melting to occur. Now, when this heat is brought into the ice cube, when we're transferring heat into the ice cube from the liquid water, what's happening is that we have a disruption of the hydrogen bonds. And I can have hydrogen bonds in water. Why? Because those hydrogen atoms can interact with the oxygen atoms of another molecule. So remember, that was one of my types of intermolecular attractions or intermolecular forces. And that's what's really keeping all of those water molecules really close together in the ice cube. So when I add heat to the ice cube, it's going to disrupt those hydrogen bonds that are holding the water molecules together. And so we're going to break or overcome those intermolecular attractions. So when ice is heated, the ice will eventually absorb enough energy to break the hydrogen bonds that hold the water molecules together. When the bonds break, so specifically this is hydrogen bonds, because in this example we're talking about water. But what I want you to think about is that you're breaking intermolecular attractions. You are breaking through these forces. So if I don't have hydrogen bonds present, I may have dipole-dipole interactions present. And that's still, if something's melting, then it's because maybe the dipole-dipole attractions are breaking apart. So it may not always be hydrogen bonds, okay? It could be any of those intermolecular forces or attractions that are keeping those molecules together. So when the hydrogen bonds break, the particles will move apart and then the ice will melt into water. We have defined then, through the breaking of these intermolecular forces, something called melting point. And the melting point of a crystalline solid, or so just a solid, is the temperature at which the forces holding the crystal lattice, so the temperature at which the intermolecular attractions holding that solid together are broken. And at that temperature, I'm going to break those attractions, and that's what makes that solid really turn into a liquid. It's really because of the breaking of those intermolecular attractions. Now, I passed out to you, I don't know that this is the exact same one, but it may be very similar. So I passed out to you a phase change diagram, and we can see here that we're plotting temperature versus energy or heat. So as I add energy, so I want to focus just on letter A right now, that's the solid. If I add energy to a system, so to a solid, I can see what's happening to the temperature. It's increasing. But at some point here, I keep adding energy, but what's happening to the temperature at this point here? It stays the same. It stays constant. It kind of plateaus. This is the point where your phase change occurs. So I can still add energy, but that energy is no longer going into helping those particles in the solid move faster. Instead, that energy is used to break the intermolecular attractions from the solid to make it into a liquid. Now, again, we've called that phase, we know that phase is called melting. So I'm adding energy, I can see that my temperature is increasing, but at some point, my temperature is going to stay the same as I continue to add energy, and at this point right here is where the phase change occurs from the solid changing into a liquid. Now, one thing that I would like you to know is that at a phase change, there is no temperature change. So when phase changes happen, the temperature stays the same. It remains constant. And that's because that energy isn't going into making the particles necessarily move faster, giving them a higher kinetic energy. Instead, that energy is going into breaking or overcoming those intermolecular attractions. So let's go back here to our PowerPoint. Okay, we also have vaporization, and that'll be the next phase change that we'll talk about. And vaporization is the process by which a liquid changes to a gas or a vapor. And you've also heard of, so there's vaporization, but you've also heard of evaporation. And those two processes are very similar, but vaporization typically happens at room temperature, and evaporation is vaporization, it's only occurring though at the surface of a liquid. So that's the difference between the two. So vaporization is the process, so that's kind of like the general category of the phase change. So the process by which a liquid changes to a gas or a vapor, and evaporation is vaporization, only it's just happening at the surface of a liquid. Okay? Now, melting as well as vaporization, these are phase changes that require energy. I need to add energy into something, so that way I can break those intermolecular attractions. So that's another thing, and I think they're all headed that way on your slides too, that these are phase changes that require energy. So melting and vaporization are two phase changes that require energy. I need to get energy into a system so that way I can break those intermolecular attractions and then have my phase change. Now, I want to go back really fast. Go. Let's go back to the phase change diagram. So vaporization, we know occurs when a liquid is changing into a gas. So if I'm going back to my phase change, I'm going to start here at my liquid. I'm going to add energy, keep adding energy or heat, and I can notice that the temperature is increasing. But at one point, that temperature is going to stop increasing. It's going to remain constant. And this, again, I'm going to continue to add energy where my temperature will stop increasing, and that's the point where my intermolecular attractions are weakening, they're breaking, and then I can go really truly from a liquid to a gas. We're going to call that, again, vaporization. So these are types of phase changes that require heat. I need to add energy before I can overcome those intermolecular attractions. Okay, so particles with enough energy can escape from a liquid and enter into a gas phase. So based on this graph here, this is just an energy distribution of molecules in a liquid. So I have number of molecules here on my y-axis, and I have kinetic energy down here on my x-axis. This graph is just showing a typical distribution of kinetic energy of molecules in a liquid, but this is specifically at 25 degrees Celsius. So the most probable amount of kinetic energy for a molecule is going to lie at the peak here. So typically, when I look at this, I can see that I have a lot of molecules here in my liquid sample. And as the kinetic energy increases, at some point, I can have some molecules, as that kinetic energy is increasing, I know that my temperature is increasing as well. So as that kinetic energy and the temperature increase, there's at some point kind of like a threshold or a cutoff where I can start to get maybe a few particles that are starting to break those intermolecular attractions, and they're moving off into that gas phase. So I can see that that happens, though, until maybe I get quite a bit more of kinetic energy. So it doesn't happen so much over here. I have to add a lot of kinetic energy before I can get into that gas phase. So that's all this graph is showing. In a closed container, the pressure exerted by a vapor over a liquid is called vapor pressure. And there's two different systems here that I want us to look at. We have an open container on this side, and then we have a closed container on this side. So in both of these containers, it's just water molecules. In the open container, I see that the water molecules here in the liquid can eventually evaporate, right, if I leave it open. So those water molecules that are in the liquid state can eventually come up through my container and evaporate, and so they can move from that liquid to the gas phase. So do you think I would have a lot of vapor pressure in an open container? I would not, because these new water vapor molecules are able to leave that container, so I don't have a lot of pressure there. But if I have a closed container, eventually, if I have my closed container, I can have some water molecules that could turn into water vapor, but where are they going to go? They don't have anywhere to go, so they're going to stay in that closed container. And since they're staying, that water vapor is staying in the closed container, it's creating a lot of pressure. And that pressure exerted by the vapor, that's what we call vapor pressure. So because I can have liquid water particles or water molecules that can move into the gas phase so they can go through the vaporization process, since it's a closed container, they have nowhere to go. So that creates a lot of pressure inside of that container. Okay, boiling point. So the boiling point is the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure. So at the boiling point, molecules throughout the liquid have enough energy to vaporize. Bubbles of vapor are going to collect like below the surface of a liquid, and then they're going to start to rise to the surface of that liquid. As the temperature of a liquid increases, these water molecules are going to gain energy. Vapor pressure is going to increase, but it's still going to be less than atmospheric pressure, and I can see that here. So I have this liquid, and I'm trying to get it to boil. It's not at its boiling point yet. So in my diagram here, the red arrows that you can see on the PowerPoint slide, the red arrows are representing atmospheric pressure, and then the black arrows that are here kind of like in between the red arrows, those are going to represent our vapor pressure. So if a liquid is below its boiling point, the atmospheric pressure is pushing on the liquid way more than vapor pressure is pushing back to the atmospheric pressure. But when a liquid is at its boiling point, when it's reached its boiling point, then the vapor pressure is going to be equal to atmospheric pressure. So the difference in these diagrams, they tried to show it based on like the sizes of the arrows. So these black arrows, which again represented vapor pressure, they aren't as large as the red arrows, which is representing atmospheric pressure. So that just represents that the atmosphere is pushing down more on the water because the vapor pressure isn't as strong enough. So at boiling point, though, I can see that the sizes of the arrows are all equal. So at boiling point, atmospheric pressure is equal to the vapor pressure. And when that happens, that's when we can get, again, our intermolecular forces are breaking, and then I'm going to have the liquid molecules turning into gas molecules. Okay, we have talked about sublimation before, and sublimation is just the process by which a solid changes into a gas without becoming a liquid. So sublimation, we are going to have to add enough energy that we can overcome so many intermolecular attractions, or the tightness of those intermolecular attractions, to quickly move it from a solid to a gas. We know that dry ice is a really good example of something that sublimes. Another example, which I don't know if your parents have some. I haven't seen any in a really long time, but mothballs. Mothballs are another thing that sublimes. Another thing that sublimes are the solid air fresheners, because if you plug in one of those solid air fresheners, over time you'll see that the little like Glade refill thing is gone. And so then that's why you have to go and get a new one, because the particles are just subliming. Now, let's say that you place liquid water in an ice tray into a freezer. So if I place liquid water in an ice tray into the freezer, what's going to happen to that liquid water? It's going to harden, right, and become ice cubes. So the liquid is now turning into a solid. So melting and vaporization, those were processes that required energy. I needed that energy to be added to a system, so then that way I could overcome or break those intermolecular attractions. We are now going to start talking about phase changes that will release some type of energy. So I want to know what will happen to the liquid water in an ice tray if I place it in the freezer. I know that it's going to solidify. So in this case, if we're moving from a liquid to a solid, we have called that what phase change? We know that's freezing. So as heat flows from water to the surroundings, the particles are going to lose energy. I just have liquid water. That heat is going to flow from the water, right? Because heat flows from a higher temperature to a lower temperature. So my heat's flowing from the liquid water into the freezer. That's my surroundings. Because of that, the liquid water is losing energy. As that liquid water is losing energy, the molecules are going to lose that kinetic energy, so their speed decreases, their velocity is going to decrease. The molecules are less likely to flow past one another. And then when I have enough energy removed from the system, the hydrogen bonds between these water molecules are going to keep those molecules fixed. Or we could say frozen into set positions. And that's what makes our ice cube. So because the particles are losing energy, they're losing that kinetic energy. They're not moving as fast because their velocity is now decreasing. And because their velocity is decreasing, they're less likely to kind of flow past one another. And it's really like these hydrogen bonds can become stronger. They can keep them more in place into that frozen type of position. Now, the freezing point, again, just kind of like the melting point, freezing point is the temperature at which a liquid can be converted into a solid. Now, when water vapor, should just say when water vapor molecules, not when a water vapor molecule. When water vapor molecules lose energy, what happens to their velocity? So when water vapor molecules lose energy, what's going to happen to their velocity? of course it's going to decrease. They're losing energy, they're not going to be moving as fast, so then that means that their velocity, of course, is decreasing. Now, the process by which a gas or vapor becomes a liquid, we know that's called condensation. And condensation is always going to involve the transfer of energy. Specifically, condensation will be a phase change that releases energy. And deposition, that's our last phase change. Deposition is the process by which we can go from a gas or a vapor, and it can turn directly into a solid. So this one's just going to be the reverse of sublimation. Okay, and let's go back to our phase change diagram here. So if I'm looking at my phase change diagram, I can see that if I'm going from a liquid to a solid, going down from a liquid, so my temperature is decreasing, at some point I'm losing energy here, and then once I get to my phase change, once I get to freezing, I'm still losing energy, but my temperature is remaining constant. And that is where my intermolecular attractions in this case are becoming stronger, because I'm losing this energy. I'm giving this energy up to the surroundings. So because of that, I can form from a liquid into a solid. And we have the same thing here when we're going through the condensation phase. I have a gas, it's losing energy, the temperature is decreasing, meaning that the velocity is also decreasing. At some point, I'm going to get to the fact where the temperature is going to remain constant. Once that remains constant, these intermolecular attractions are becoming stronger, strong enough to make that gas now into a liquid. Okay, so last part of this phase change section is something called phase diagrams. And there are two variables that combine to control the phase of a substance. So two really important things that will control the phase of a substance. The first one is temperature, and then the second variable is pressure. A phase diagram is a graph of pressure versus temperature that shows in which phase a substance will exist under different conditions of temperature and pressure. So temperature and pressure are the two variables that are really going to control the phase of a substance. And this is an example of a phase diagram here. So let's just kind of maybe go through and look at this. This is specifically a phase diagram for water. And we can use a phase diagram to predict maybe what phase water will be in any combination of pressure and temperature. So there are three different regions always in a phase diagram. You're going to have a region representing the solid, you have a region representing the liquid, and then a region representing vapor or gas. There are going to be three curves that will also separate the regions from one another. So I have kind of like a red line here, so this is my red curve, and this is just separating the solid from the liquid phase. I have a blue line right here, or we'll call that a blue curve, and that's representing the vapor from the liquid phase. Then I have this really small little yellow line down here, and that's separating the solid from the vapor phase. So I have three different sections with three different curves to separate and represent those three regions or three areas. Now, there's a point A and a point B on your phase diagram, and that will always be true for every phase diagram. You'll have two specific points that are super important for us to locate. The first point, letter A, is right here, and this letter A is called the triple point. The triple point is the point on a phase diagram that represents the temperature and pressure at which all three phases of a substance can coexist. So I can see here, this is where my line for separating the liquid and solid meets the line separating the liquid from the vapor, meets the line representing the solid from the vapor. So at this point, all of my phase changes could possibly occur at this point. So this is a triple point. And again, just represents I could have a solid, a liquid, or a vapor. They can coexist. Now, there's a second point, point B, and it's all the way up here, point B. That's called the critical point. And the critical point is just the point that indicates the critical pressure and critical temperature above which a substance couldn't exist as a liquid anymore. So typically once we get past this critical point, past this point B, a lot of times in phase diagrams we'll see that that's what gets us into the state of plasma at really unbelievably high temperatures and sometimes high pressures as well. So critical point, again, is just that point of critical pressure and critical temperature above which something, a substance, can exist as a liquid. Okay, so we have triple point, we have critical point, and a phase diagram is just showing us how a substance can exist in pressure and temperature if it's a solid, a liquid, or a gas or vapor. Okay, and then I think this is our last slide, guys. Yeah. So the phase diagrams are different for different substances. So every substance has its own phase diagram, and there are no two phase diagrams that are identical. So everyone is always going to be different. However, we know that phase diagrams are going to supply really the same type of data for us because we're always going to be able to determine, based on this pressure and this temperature, is, for example, carbon dioxide. Is it going to act like a gas, or is it going to act like a solid, or is it going to act like a liquid? And I can look at the same thing here for carbon. So Monday in class, I'm going to give you an example of a phase diagram, a few examples, so that way we can kind of like read some of these together, okay? And on Monday, we're also going to move into our mixtures and solutions chapter, which is chapter 14 in your book. So I hope you guys have a really great weekend, and I'm very excited that I'm here at school and I have not seen the mouse yet, Murray the mouse. Have a good weekend, guys. Bye.